Okay, so let's have a look at the solution for 8.2. A structural steel solid bar experiences a tensile load of 50 kilonewtons. The bar has a diameter, so it's again a circular bar of 20 millimeters. Young's modulus is 200 gigapascals. Calculate the tensile stress experienced in the bar and the change in length under this condition. It sounds like just the same as the last question we looked at and what the answer's looking for. So 159 megapascals and 4 millimeter extension. Okay, so be a bit careful here. Now we're doing changing length and not just strain. Whereas before we was doing strain. So that's the only difference between the two questions. So for part A, tensile stress, so you should be able to, or at this stage maybe, to jump from knowing that force divided by area, if I'm dealing with a circular bar, is going to end up as 4F over pi d squared. Okay, so look at the previous solution, how I got there. So now I can put in my numbers. So 4, get rid of my prefixes and my units where necessary. So we got 50 kilonewtons, so 50,000 going in there. Pi, the diameter is 20 millimeters. I let the calculator do the conversion for me. So I'm going to put in 20 to the minus 3, and I'm going to square that in my calculator. So my calculator, it will do the units conversion for me. So let's just put that in. So we're going to have 4 times 50,000, and then we're going to have a pi times 20 to the power 10 to the power minus 3, and then I want to square all that number. Again, I get this very long number, so let's press the eng button to try to make sense of what that is. So it's saying it's a 159 point blah 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 stuff times 10 to the power 6. On the whole, when you're dealing with stress, we just restate the answers in terms of a whole number of megapascals. So here 159 1 5, so that would be that number to the 10 to the 6, which is going to be equal to 159 megapascals, or 159.15 megapascals. Normally I'd probably state answers in terms of megapascals. Okay, for part B, so we're looking for change in length. So we think to ourselves, what's an equation with change in length in it? Well, I've got the strain is equal to the change in length divided by the original length. We're looking for the change in length, so change in length equals strain times by the length that I'm looking at. How do I get the strain? Well, I know that strain is, I'll probably have to jigger around with some formulae here. So at the moment, I'm going to stop there. The other formula that I know is that Young's modulus is stress over strain. So therefore strain is going to be stress divided by Young's modulus. So I can combine these two things here and here, and then we're going to get that the change in length is going to be the stress times by the original length divided by the Young's modulus. So now I've got a formula where I can put my numbers in from the question and then put this straight into the calculator. So the stress we've already found. We want to use the more accurate number. So 159. For workings on the whole, workings something to 10 to 5 sig fig, and given answers to 3 sig fig usually will be fired in an engineering calculation. So we get rid of the mega and put in times 10 to the 6. Well, we're going to put that into calculator. The length is 5 meters. The Young's modulus is 200 giga. So now we're ready to put that into our calculator. So let's open up one of them. So 159.15 times 10 to the 6 times that by 5. Now go 200 like times 10 to the 9. Let's press equal. So we want to be stating our answers in a sensible unit. So we've already got sensible units here, times 10 to the minus 3. So I know I'm in SI units, so something times 10 to the minus 3 is a millimeter. So I could say 3 point, let's write this out to 5 sig fig first, 9, 7, 8, 8, rounding up the other 7, times 10 to the minus 3. And so rounding this to a nearest millimeter would be 4 millimeters. Okay, so that's 8.2.